All right, everyone, welcome back. Today we are taking another deep dive, and let me tell you, this one's a brain tickler. We're tackling Merkle trees and hashing, two things that sound way more complicated than they actually are.
Absolutely. And they're essential to understanding how blockchains manage to be both incredibly secure and surprisingly efficient.
Right, so for anyone who's ever wondered how millions of transactions can happen securely, well, it all comes down to these elegant systems.
That's right.
So let's start with Merkle trees. What exactly are we talking about when we say Merkle tree? I mean, it sounds like something out of a Tolkien novel.
Well, imagine instead of having to go through every single transaction one by one, what if we could organize them like a really efficient digital filing system?
Okay.
That's essentially what a Merkle tree does.
So bringing order to the chaos.
Precisely. So we take these individual transactions and we group them together, and then we group those groups together and so on and so forth. And each of these groups gets its own unique code, a hash. You've probably heard of that. It acts as a label for that specific set of data.
Okay, so it's kind of like organizing a library, right? Instead of books, we've got transactions. Each shelf, each section has its own unique code that represents everything on it.
You've got it. And just like finding a book on a particular shelf is a lot easier than searching the entire library, Merkle trees make verifying transactions incredibly fast.
That makes a lot of sense, actually. But how does this help in, like, the real world of blockchain?
Imagine trying to verify a single transaction in a blockchain that's got millions of transactions in it. Trying to search through all of that would be a nightmare.
Yeah, absolutely.
It'd be like trying to find a needle in a haystack. But with a Merkle tree, you don't have to. You can actually prove that a transaction is included in a block without needing to see every single transaction ever made.
Oh, wow. So, like, how much faster are we talking?
Well, let's take Bitcoin as an example. To verify a single Bitcoin transaction, if you didn't have a Merkle tree, you'd need to download the entire blockchain, which is, well, hundreds of gigabytes of data.
Yay.
But with a Merkle tree, you can do it with just a few kilobytes.
Wow. That's amazing.
Yeah, and it takes just a fraction of a second, so it's incredibly efficient.
So we're talking about massive time savings and resource savings, all thanks to this clever organization.
Exactly. That's the power of the Merkle tree, and that's why it's so essential for blockchains, especially as they grow larger and larger.
Okay, so we've got these Merkle trees, right? Like, they're bringing order to this whole blockchain universe. But let's talk about the engine that actually makes it all work, hashing.
Yeah, hashing. It's really quite clever when you get down to it.
So it's more than just, like, assigning a code to a piece of data.
It's way more than that. Think of it this way. Every piece of data could be a tiny transaction or like a whole encyclopedia gets fed into this special algorithm.
Yeah.
And this algorithm, there are a bunch, but a popular one is called SHA-256. And it spits out this fixed length code. That's your hash.
Right, the digital fingerprint. But how does that actually stop someone from messing with the data?
Okay, so these hashing algorithms, they're designed to be what we call a one-way function.
One-way functions.
Yeah, so it's really easy to create a hash from a piece of data, but it's practically impossible to go the other way around. Like, you can't take the hash and recreate the original data.
So I can scramble the eggs, but I can't unscramble them.
Exactly. A very messy analogy, but
Yeah.
yeah, pretty much. And here's the really cool part. Even the smallest change to the data, I'm talking like swapping a single letter in a document, it's going to completely change the hash.
Whoa, really?
Oh yeah, we call this the avalanche effect. It's actually what makes blockchains so incredibly secure.
How so?
Because any attempt to mess with the data, even just a little bit, it changes the hash, which then ripples up through the Merkle tree, and boom, alarm bells are going off all over the network.
It's like this invisible web of security.
Exactly. And to make things even more secure, these hash functions are what we call deterministic. It means that the same input will always produce the same exact output every single time. So anyone, anywhere, can check if a block is valid.
And how do they do that?
They just run the data through the hashing algorithm and compare it to what's on the blockchain. If it matches, you know everything's legit.
So it's like a universal truth checker built into the system.
Exactly. And this is where the elegance of Merkle trees really shines, you know? You don't need to check every single transaction. You just follow those hashes up the tree, and if that final hash, that Merkle root, if it matches what's on the blockchain, you're good to go.
That's amazing. So we've got efficiency and security all wrapped up in this elegant package.
Exactly. It's no wonder blockchain can handle so much data without compromising on security. It's really quite remarkable.
All right, so we've talked about Merkle trees, like this super efficient way to keep everything organized,
Yeah.
and hashing, which is like the tamper-proof seal on all of this data.
Right.
But where does mining fit into all of this? Because I know it's all connected somehow.
It is.
It's all like one big, happy blockchain family.
Well, it all comes together really in that mining process.
Right.
Remember how we were talking about miners competing to solve those complex mathematical problems?
Right, like racking their brains.
Well, those problems are all about finding a specific hash for a block of transactions.
So they're trying to, like, what, guess the right hash?
Kind of. They're actually looking for what we call a nonce.
A nonce? What is it?
It's like a special key, and when you combine it with the block's data and run it through the hashing algorithm,
Right.
it spits out a hash that meets very, very specific criteria. And these criteria are set by the network.
Okay, so it's like trying a bunch of different keys to unlock a door.
Yeah,
And the first one to find the right key, boom, they get to add the next block to the blockchain.
you got it. And the more miners there are, the more people out there rattling those keys, the faster this process happens. And that speed, that's what we call the hash rate.
Right. So the higher the hash rate, the more secure the blockchain.
Exactly. Because if someone wanted to go back and tamper with old transactions, they'd have to redo all that work. Imagine finding new hashes for every single block, all while competing against the entire network.
Talk about an impossible task.
It'd be like trying to outrun a cheetah. You might be fast, but the network is always faster.
Right. So you've got the Merkle trees keeping everything organized. You've got the hashing, making sure no one's messing with the data. And then you've got the miners constantly verifying and securing everything. It's actually really, really quite amazing when you think about it.
It is, and it all comes down to this beautiful interplay between Merkle trees and hashing.
They really are the unsung heroes of the blockchain world, wouldn't you say?
Absolutely. Without them, none of it would be possible, at least not on a global scale. And, the beauty of it is these concepts, they're not limited to cryptocurrency. They have applications in all sorts of fields.
That's right. From supply chain management to, like, digital identity, who knows what the future holds. So to everyone listening, keep those thinking caps on and keep exploring. This blockchain world, it's full of surprises. And that's it for this deep dive. We'll see you next time.